Okay.
It's a pleasure to introduce Tatiana Abdul-Naim from University of Oklahoma. She'll be talking about cohomology of congruence subgroups. Please.
Thank you for the invitation to speak and for organizing this session. I'm going to talk about the cohomology of congruent subgroup gamma 0 n of p. This talk is oh. So this talk is split into two parts. The first part, I'll talk about the top dimensional cohomology, and then in the second part, I'll talk about other high degree cohomology. So to introduce the main object of this talk, p is a prime number, and n is a positive integer, at least one. So this subgroup, gamma 0 n of p, this is a subgroup of SLNZ, whose elements have this following form, mod p. So the special thing about this group is that just the first column is a multiple of E1. So this first entry doesn't have to be 1. It can be any non-zero element as long as the determinant is still equal to 1. The goal of this talk is to understand as much as possible the cohomology in degree n choose 2 of this subgroup with rational coefficients. I will explain in a bit why I'm interested in the degree n choose 2 in particular. The cohomology groups of this subgroup are important in algebraic K theory and algebraic number theory. And in fact, for n equals 2, cohomology classes in here, they come from certain modular forms. And for higher n's, they come from a generalization of modular forms. There are also other connections as well, but my knowledge is very limited when it comes to it. But what I'm trying to say is understanding this group gives a topological approach to number theory. So to start off, a fundamental result by Borel and Serre, they showed that for any finite index subgroup gamma of SLNZ, we have an isomorphism between the cohomology in degree n choose 2 minus k of gamma and the homology in degree k of gamma with some twisted coefficients. So for now, just think of these coefficients as a big SLNZ module. I will talk about them a bit more later. And this isomorphism is for any k. So k can be anything. So in particular, if we look at the cohomology in degree k of gamma with q coefficients, and then k is anything that is bigger than n choose 2, then with this isomorphism, we get a vanishing result here. So this n choose 2 is the highest degree in which we might possibly have non-zero classes, and so we refer to it as the top degree. So now the goal was to compute the cohomology in degree n choose 2, and now with this Borel and Serre isomorphism, we have homology in degree 0 of gamma now with these twisted coefficients. And by definition, this is the coinvariance. And if you're not familiar with the coinvariance definition, so if you have a group G acting on M, then you can define the coinvariance M sub G to be the quotient of M by all the elements of the form Gm minus M. And this is the largest quotient on M on which G acts trivially. So now the goal is to understand these coinvariances. And so to do so, we want to understand this big SLNZ module. So I'm going to define it for any field F. Just a quick recall on the definition of the Tietz building. So the Tietz building is a simplicial complex whose vertices are non-zero proper subspaces of F to the n. and whose case simplices are given by inclusions of this form. And then you can also observe that with this definition, the Tietz building comes from a poset. Solomon and Tietz, they showed that the Tietz building is homotopy equivalent to a wedge of n minus 2 spheres. And if the field is finite, we can actually know how many spheres we have in here. But now with this homotopy equivalence, we have that the Tietz building has only one non-zero reduced homology. And so this gives the definition of the Steinberg module. It is defined to be the reduced homology in degree n minus 2 of the Tietz building. And if F is Q, then SLNZ acts on these non-zero subspaces, these non-zero proper subspaces, and this action preserves the inclusion, and so it induces an action on the Tietz building, and hence induces an action on the Steinberg module. So this Steinberg module is an SLNZ module. Okay? So now recall the goal is to compute these cohomology groups, which we said they're isomorphic to the coinvariance of the Steinberg module. And now the way to approach this goal is the following. So if we look at this map here, let's ignore the homology for a second, and then we always have a surjective map from the Tietz building to the Tietz building mod gamma. And so this map induces a map on the homology. But now the left-hand side is by definition the Steinberg module. And since the coinvariance is a quotient of the Steinberg module, we get a surjective map this way. And this gamma acts trivially on the right hand side, and so by universal property, we get a map going up this way. So now we have a map psi going from our goal to the homology of the Tietz building mod gamma. And so a way now to understand these coinvariants is by understanding the homology of the Tietz building mod gamma and this map psi. And the reason we do so, and we don't directly go into computing the coinvariance, is that this object tends to be hard to compute directly. But the Tietz building mod gamma tends to be an easier object to work with. And it turns out that in this case, it has a very simple description. So I'm going to consider the order complex corresponding to the poset Tietz building mod gamma. And here I'm thinking of the Tietz building as a poset, since I said earlier that it does come from a poset. So I'm thinking of the poset, and then I'm quotienting by gamma, and then I look at the corresponding simplicial complex. So the vertices in the Tietz building are non-zero proper subspaces. So their dimensions range from 1 to n minus 1. So these bullets represent the dimensions of the subspaces. And for each dimension, we get 2 orbits. So now I have 2 bullets in each dimension. So the first collection of the bullets is given by the subspaces not containing the vector E1 mod P, and then the second collection corresponds to the subspaces containing the vector E1 mod P. And this all goes back to how gamma is defined. We still have the simplices, which we said are given by inclusions. And so these bars, these lines right here, represents the inclusions that we get in this quotient. So now we look at this, and we see that if n is 2, then we're only going to have these 2 bullets at the bottom. And so the space is going to be a discrete set of 2 points. However, when n is at least 3, we have at least these 4 points with these 3 inclusions, and so the space is contractible. And so we have this, and hence the homology is 0 for n at least 3, and it's Q for n equals 2. So now we fully understand this right object here, and now the question is, when is the map psi an isomorphism? It turns out we have the following. So this is the main theorem. Psi is always surjective, though it's very clear that it's surjective for n at least 3, but it's also surjective for n equals 2. It is injective if P is in this list of prime numbers, or P is bounded by 6n minus 14. Now, if you look at this bound, there is an overlap between this list and this bound. Because, for example, if you take n equals 3, then you will recover the primes 2, 3. However, this statement, like listing the prime numbers this way, is a better statement. Because here I'm saying that this is injective for all n if P is in here. And it is not injective for n equals 2, 3, and P not in this special list of prime numbers. I also show that we have a full description for n equals 2. So for n equals 2, n choose 2 is 1. So now we're looking at the dimension of h1 of gamma 0, 2. And we have this full description, so we know exactly what happens for each prime number. And now we see for P equals 2 and 3, it is 1. For P equals 13, it's also 1. 5, 7, it's also 1. And so this guy, and so the domain of psi is Q, and then the codomain is Q, and so we do get the isomorphism for this special list of prime numbers. Now, this full description for n equals 2 is not a new result. This is already known to number theorists. They compute this using modular forms. I did the computation using chain complexes, so it was a completely different approach. So now just to parse what happens in the theorem. So I'm looking at the prime numbers from 2 to 13 and n from 1 to 6. The first row is Q, just because we're looking at n equals 1, so this is always Q. Now all for n equals 2, this comes out from the full description. Although for the prime numbers 2, 3, 5, 7, 13, we can also deduce this from the isomorphism of psi. And then all the other zeros come out from the isomorphism of psi. So this was all new. We get all these new zeros and all these by degrees. And all the red values. So I directly computed the cohomology in for these specific prime numbers, 11, 17, and 19. And then we see there's some kind of pattern here. So for example, if you look at 11, we start with q cubed for n equals 2, and then it goes to a q squared, and then q, and then 0. And then similarly for 17 and 19. And so you can wonder whether we still have this pattern for other prime numbers. And so an open question is, what happens for other cases? Oh. And so, okay, so now I'm going to talk a little bit about the proof outline. The proof uses a presentation of the Steinberg module, which is originally done by Bykovsky using generators and relations, though the proof uses a slightly different version of this presentation. This is due to Church and Putman. They showed that there are concrete simplicial complexes, Xn prime, a subcomplex of Xn, with an action of SLNZ, such that this following sequence is an exact sequence. And so this map right here is just the boundary map, just the differential going from the n chains to the n-1 chains. And I did say the Steinberg has generators and relations, and so basically they construct the sequence using generators in this term right here, and then using relations right here. And the reason I want to use this presentation is because, so I'm interested in coinvariants, and the coinvariants are a right exact functor. And so now, if I take coinvariants everywhere, I still preserve exactness. So now we have this exact sequence. I'm going to call this boundary map here del. And now with this exactness, we have that the coinvariants are isomorphic to the co-kernel of this map. And then it turns out that this is isomorphic to the n-1 relative homology of xm mod gamma and xm prime mod gamma. So now with this isomorphism, the map psi is a map going from this relative homology to the homology of the Tietz building mod gamma. And this map factors through this term. Now, where does this come from? So the map on the left is just the boundary map from the long exact sequence of homology. It's right here. And then this map phi, I'm not going to focus on too much, but this is some poset map. Just looking at simplicial complexes as posets. I want to talk about this map coming from the long exact sequence of homology. So we want to show psi is an isomorphism. So that means we want this boundary map and the map phi to be isomorphisms. And this boundary map is an isomorphism if the term on the left in the long exact sequence and the term on the right in the long exact sequence vanish. And so for these two terms to vanish, I proved that xn mod gamma is always n-2 connected, and this will give the surjectivity part. And I showed that it is sometimes n-1 connected, and this sometimes depends on n and p, and this gives the injectivity part. And most of the paper was just proving this theorem because it was the most complicated part. So we have that xn mod gamma is connected in some range. Okay, so this is the end of the first part, talking about the top degree cohomology. Now for the other part, other high degree cohomology. So Ash, Miller, and Pabst proved that if you take the direct sum of homology in degree k of GL and Z with Steinberg coefficients, and if you take the direct sum with Steinberg coefficients tensor a determinant representation, I'm going to call this H and this H determinant. So now they show that these two are Hopf algebras. And so what I show, I'm going to look at the congruence subgroup. Now, this is a slightly different version than the group I was dealing with in the first part. So here I'm looking at the subgroup of GL and Z. The only difference between this group and the group in the first part of the talk is that here I'm allowing determinant -1. But we're gonna see later that there is a connection between this group and the other group, and how we can deduce information from here to the subgroup of SLNZ. So I take the direct sum of the homology of gamma 0 and plus minus now with standard coefficients, and the direct sum of the homology with standard coefficients tensor determinant representation. And I showed that these two are Hopf modules over each of H and H determinant. So I show H gamma is Hopf module over H, and then H gamma determinant is a Hopf module over H gamma. And now the way I want to use this information, this is a fundamental result of Hopf modules due to Sweedler. If you have two Hopf modules, then they are free modules. So now I have that H gamma and H gamma determinant are free modules over H and H determinant respectively. What this means is that now classes in low degree generate classes in high degree. So if I have classes in low degree and H gamma, I can use this freeness to get classes in high degree in H gamma. And so this is done the following way. So I'm going to look at the transfer map from the homology of the GLNZ to the homology of gamma 0 and plus minus. And I'm going to denote the image of any x in the homology of GLNZ by x gamma. And so this first table right here, this is information that we already know about the homology of GLNZ. So what are these notations? For n odd, Brown and Schnetz showed that there are some classes Wn in homology of GLN-Z with Tamer coefficients in degree n. And these are called the wheel classes, if you ever heard of if you're familiar with them. And I'm also going to consider the trivial classes Tn. So Tn are classes in homology in degree n choose 2 of GL&Z with Tamer coefficients. But by Borel and Serre, this is just the cohomology in degree 0. So they're just trivial classes. So now we have these classes in this picture. We have T1, W3, and then you can multiply T1 and W3 and get a class right here. And then we have W4. So this is just a GL&Z. But now using the freeness, we get this following diagram for gamma 0 n of p. So T1 gamma is the image of T1 under the transfer map. And now with the freeness, I can multiply T1 gamma with T1 and get a new class in pi degree 2, 0. So now all these blue classes, we get them by freeness. And these are classes that were not known before. And all the classes in the black ink, we get them by the transfer map. So this is homology of gamma plus minus with Tamer coefficients. Now we have a similar picture with determinant coefficient. So these are classes in GL&Z. And now we get corresponding classes in gamma 0 plus minus. So now the green classes are the classes that we get from freeness. So I'm multiplying T2 gamma by T4, and then I'm getting a class right here. And so the way I want to connect this to the first part of the talk. So looking at the isomorphisms here, the homology of gamma 0 and so now here there's no plus minus. So this is the subgroup of SL and Z with Tamer coefficients. It is equal to the sum of the homology of gamma 0 plus minus with Tamer coefficients plus homology with Tamer coefficients tensor determinant coefficient. So that means if I know classes in each of these summons, then I can just combine them and get a big picture of gamma 0n. And that's exactly what we have here. And so now what I have is I have new classes in homology in degree k of gamma 0 n of p with standard coefficients. But this recall is just the result of Borel and Serre. They showed that homology of degree k with standard coefficients is just cohomology in degree n choose 2 minus k with q coefficients. So now, so the first part was taking care of k equals 0. And now here we know a bit more what happens when k is not necessarily 0. And so we have new information about this as well. And this is the end of my talk. Thank you.
Thank you very much for your very interesting talk. Any question? Actually, I will stop recording. I will stop recording now, but